Let's look at using Excel to do some of our calculations when we're exploring the behavior of a sequence of numbers. So let's say I have this specification of a sequence, and let's say it says starting at n equals 0. We'll put that up here. Suppose we're wondering what's the limit as n goes to infinity, and what's the overall behavior, not just the limit. So because this is a fraction, a lot of the sequences we deal with have fractions in them. It's often interesting to see the numerator separate from the denominator. So I would suggest putting each in its own column and then the result that divides the numerator by the denominator. And then that's really what I would graph. So for the numerator here, I'm going to go 10 to the n. And for the denominator, I'm going to say fact of n. Fact is how you do factorial in Excel. Factorial of 0 is 1. That's a good thing to remember. And then for the result, we'll do the numerator divided by the denominator, which is pretty boring right now. But then I'll fill this down or paste it down. And so the numerator got bigger, the denominator stayed the same. Let's do this a few more steps out. So the numerator is growing by a factor of 10 every time. Pretty much expect that. The denominator is growing, it's just factorials, and it looks like the result is growing pretty quickly. So what can we say about the limit as n goes to infinity? Right now it looks like the limit is going to be infinity, but 5 is not all that close to infinity. Maybe we should go out even farther, and let's try that here. So there we see the result, the ratio of the two keeps getting bigger, but now it's actually getting smaller again. So let's go do that a little bit more. Now the ratio is down below 1. It's a good idea to graph this. Let me show you what happens if you do. If you just click somewhere in the middle here just once, or I mean just highlight one cell and insert scatter plot, and I like to do markers with connecting straight lines for this. So the numerators are getting big by a factor of 10 each time. The denominators are also getting big. So that's really making it hard to see what's going on, because that last one is so big, the scale gets squished for everything else. So I'm going to click on that and hit the delete key, and that deletes the series from the graph, but not from the table. And again, there's something so large I can't see what's going on, so I'm going to click on that and hit the delete key. So now the only thing I have is the actual sequence itself, and it looks like it was getting quite big up until about n equals 9 or 10 or so, and then it started falling off and seems to be hopefully or maybe approaching a limit of 0 as n goes to infinity. So I know sometimes our book says like plot the first 5 results in the sequence, but you can't always trust that the first 5 are going to be indicative of the behavior of the whole thing. You have to think about what's going on in these formulas. Like what is n factorial and what is 10 to the n? Let's say at n equals 13. So 10 to the n would be what? 10 times 10 times 10. Let's do this. So that's 6, 9, 12, and another 10. What is n factorial? It's 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10. So you can see each of these is smaller than each of these. So it seems like this top one is kind of winning, because each time the corresponding term here versus there is bigger. But once we get above 10, we can see that here the 10 to the n is just multiplying by 10 every single time. But now the n factorial is multiplying by things bigger than 10, and those are just going to keep getting bigger and bigger, while this is going to keep being just 10. So in the long run, the n factorial catches up with and passes the 10 to the n. So factorials grow faster than exponentials. That's an important thing to keep in mind here.